3.0 Introduction. In this chapter, we develop the Z-transform representation of a sequence and study how the properties of a sequence are related to the properties of its Z-transform. The Z-transform for discrete time signals is the counterpart of the Laplace transform for continuous time signals, and they each have a similar relationship to the corresponding Fourier transform. One motivation for introducing this generalization is that the Fourier transform does not converge for all sequences, and it is useful to have a generalization of the Fourier transform that encompasses a broader class of signals. A second advantage is that in analytical problems, the Z-transform notation is often more convenient than the Fourier transform notation. 3.1 Z-transform. The Fourier transform of a sequence xn was defined in Chapter 2 as x, EJW, equals 00 Lxn EJFN. 3.1, n equals 00. The Z-transform of a sequence xn is defined as x, z, equals 00 Lxn Zn. 3.2, n equals 00. 100 Chapter 3. The Z-transform. This equation is, in general, an infinite sum or infinite power series, with z considered to be a complex variable. Sometimes it is useful to consider EQ, 3.2, as an operator that transforms a sequence into a function. That is, the Z-transform operator z, defined as 00 z, xn equals Lxn Znx, z, 3.3, n equals dash, xj transforms the sequence xn into the function x, z, where z is a continuous complex variable. The unique correspondence between a sequence and its Z-transform will be indicated by THC notation xnx, z. 3.4, the Z-transform, as we have defined it in EQ, 3.2, is often referred to as the two-sided or bilateral Z-transform, in contrast to the one-sided or unilateral Z-transform, which is defined as 00x, z, equals Lxn Zn. 3.5, n equals 0. Clearly, the bilateral and unilateral transforms are identical if xn 0 for nLt 0, but they differ otherwise. We shall give a brief introduction to the properties of unilateral Z-transform in section 3.6. It is evident from a comparison of x 3.1 and 3.2 that there is a close relationship between the Fourier transform and the Z-transform. In particular, if we replace the complex variable z in EQ, 3.2, with the complex quantity ej, then the Z-transform reduces to the Fourier transform. This is the motivation for the notation x, e, for the JW Fourier transform. When it exists, the Fourier transform is simply x, z, with z equals e. This corresponds to restricting z to have unity magnitude, i.e., for is I equals 1. The Z-transform COR responds to the Fourier transform. More generally, we can express the complex variable z in polar form as JWZ. With z expressed in this form, EQ, 3.2, becomes 00x, reg w, equals Lxn, reg w, n equals 00. Or 00x, reg w, equals L, xnRn, EJWN. 3.6, n equals 00 equation, 3.6, can be interpreted as the Fourier transform of the product of original n sequence xn and the exponential sequence r'. For r equals 1, EQ, 3.6, reduces to the Fourier transform of xn. Since the Z-transform is a function of a complex variable, it is convenient to describe and interpret it using the complex z-plane. In the z-plane, the contour corresponding to ISL1 is a circle of unit radius, as illustrated in figure 3.1. This contour, referred to as the unit circle, is the set of points z edge for 0, WLT2T. The Z-transform evaluated on the unit circle corresponds to the Fourier transform. Note that W is the angle between the vector from the origin to a point z on the unit circle and the real axis. Section 3.1 Z-transform TMZ plane 1 refigure 3.1 the unit circle in the complex z-plane. of the complex colon plane. If we evaluate x at points on the unit circle in the colon plane beginning at equals 1, i.e., w equals 0, through j, le, wjr/2, to z equals -1, i.e., wjr, we obtain the Fourier transform for 0 w junior continuing around the unit circle would correspond to examining the Fourier transform from w equals jr to w equals 2jr or, equivalently, from w equals jr to w equals o. In Chapter 2, the Fourier transform was displayed on a linear frequency axis. Interpreting the Fourier transform as the colon transform on the unit circle in the colon plane corresponds conceptually to wrapping the linear frequency axis around the unit circle with w equals 0 at equals 1 and wjr at -1. With this interpretation, the inherent periodicity in frequency of the Fourier transform is captured naturally, since a change of angle of 2jr radians in the z-plane corresponds to traversing the unit circle once and returning to exactly the same point. As we discussed in Chapter 2, the power series representing the Fourier transform does not converge for all seconds, i.e., the infinite sum may not always be finite. Similarly, the colon transform does not converge for all sequences or for all values of z. For any given sequence, the set of values of for which the colon transform power series converges is called the region of convergence, ROC, of the colon transform. As we stated in section 2.7, if the sequence is absolutely summable, the Fourier transform converges to a continuous function of w. Applying this criterion to EQ, 3.6, leads to the condition 9, reg w, 1L009 NRNLLT00, 3.7, LL equals 00 for convergence of the z-transform. From EQ, 3.7, it follows that, because of the multiplication of the sequence by the real exponential r', it is possible for the colon transform to converge even if the Fourier transform, r equals 1, does not. For example, the sequence xn is not absolutely summable, and therefore, the Fourier transform power series does not converge absolutely. However, R nu n is absolutely summable if RGT1. This means that the colon transform for the unit step exists within ROC R11 GT1. Convergence of the power series of EQ, 3.2, for a given sequence depends only on 1 since 9ILT00 if L009 and 2INLT00, 3.8, n equals 00 i.e., the ROC of the power series in EQ, 3.2, consists of all values of z such that the inequality in EQ, 3.8, holds. Thus, if some value of z, say, equals 1, is in the ROC. Chapter 3 The Z-transform 1 I'm Z-plane Figure 3.2 The ROC as airing in the Z-plane. For specific cases, the inner boundary can extend inward to the origin, and the ROC becomes a disk. For other cases, the outer boundary can extend outward to infinity, then all values of z on the circle defined by I z equals is 1 will also be in the ROC. As one consequence of this, the ROC will consist of a ring in the z-plane centered about the origin. Its outer boundary will be a circle, or the ROC may extend outward to infinity, and its inner boundary will be a circle, or it may extend inward to include the origin. This is illustrated in Figure 3.2. If the ROC includes the unit circle, then this of course implies convergence of the z-transform for ISL1, or equivalently, the Fourier transform of the sequence converges. Conversely, if the ROC does not include the unit circle, the Fourier transform does not converge absolutely. A power series of the form of EQ, 3.2, is a Laurent series. Therefore, a number of elegant and powerful theorems from the theory of functions of a complex variable can be employed in the study of the Z-transform. See Brown and Churchill, 2007. For example, a Laurent series, and therefore the Z-transform, represents an analytic function at every point inside the ROC, hence, the Z-transform and all its derivatives must be continuous functions of Z within the ROC. This implies that if the rock includes the unit circle, then the Fourier transform and all its derivatives with respect to W must be continuous functions of W. Also, from the discussion in section 2.7, the sequence must be absolutely summable, i.e., a stable sequence. Uniform convergence of the Z-transform requires absolute summability of the exponentially weighted sequence, as stated in EQ 3.7. Either of the sequences xdn equals sin when -00 ltn lt00, 3.9, nn and x2n cos von -00 ltn lt00, 3.10, is absolutely summable. Furthermore, neither of these sequences multiplied by Rn would be absolutely summable for any value of R. Thus, neither of these sequences has a Z-transform that converges absolutely for any Z. However, we showed in section 2.7 that even though a sequence such as x1n in EQ 3.9 is not absolutely summable, it does have finite energy, Le, it is square summable, and the Fourier transform converges in the mean square sense to a discontinuous periodic function. Similarly, the sequence x2n in EQ 3.10 is neither absolutely nor square summable, but a useful Fourier transform for x2n can be defined using impulse functions, i.e., generalized functions or Dirac delta functions. In both cases, the Fourier transforms are not continuous, infinitely. Section 3.1 S at OEFR at RIE, ICSSSTE9, I transform 103 differentiable functions, so they cannot result from evaluating a Z-transform on the unit circle. Thus, in such cases it is not strictly correct to think of the Fourier transform as being the Z-transform evaluated on the unit circle, although we nevertheless continue to use the notation x, EJW, always to denote the discrete time Fourier transform. The Z-transform is most useful when the infinite sum can be expressed in closed form, i.e., when it can be summed and expressed as a simple mathematical formula. Among the most important and useful Z-transforms are those for which x, z, is equal to a rational function inside the rock, i.e., p, z, 3.11, x, z, equals q, z, where p, z, and q, z, are polynomials in Z. In general, the values of Z for which x, z, equals 0 are the zeros of x, z, and the values of Z for which x, z, is infinite are the poles of x, z. In the case of a rational function as in EQ 3.11, the zeros are the roots of the numerator polynomial and the poles, for finite values of Z, are the roots of the denominator polynomial. For rational Z-transforms, a number of important relationships exist between the locations of poles of x, z, and the rock of the Z-transform. We discuss these more specifically in section 3.2. However, we first illustrate the Z-transform with several examples. Example 3.1 Right-sided exponential sequence. Consider the signal xn equals anu n, where a denotes a real or complex number. Because it is non-zero only for n::, 0, this is an example of the class of right-sided sequences, which are sequences that begin at some time nl and have non-zero values only for nl:, nlt00, i.e., they occupy the right side of a plot of the sequence. From EQ 3.2, 0000x, z, equals L anu n zn equals L, azl, nn equals 00n equals O for convergence of x, z, we require that 00 L lis LLN LT00. N equals O. Thus, the rock is the range of values offs for which lis LLT lor, equivalently, is LGT lal. Inside the rock, the infinite series converges to 00 in 1 zx, z, equals, az, equals dash, is LT lal. 3.12, 1 azlzan equals O. To obtain this closed form expression, we have used the familiar formula for the sum of terms of a geometric series, see Jolly, 1961. The z-transform of the sequence xn equals anu n has n rock for any finite value of lal. For a equals 1, xn is the unit step sequence with z-transform 1x, z, equals -1 isa gt1. 3.13, 1c if lal lt1, the Fourier transform of xn equals anu n converges to 1x, ejw, equals 3.14, 1a ejw. 104 Chapter 3 The z-transform however, if a 2, 1, the Fourier transform of the right-sided exponential sequence does not converge. Figure 3.3 Pole 0 plot and rock for example 3.1. In example 3.1, the infinite sum is equal to a rational function of z inside the rock. For most purposes, this rational function is a much more convenient representation than the infinite sum. We will see that any sequence that can be represented as a sum of exponentials can equivalently be represented by a rational z-transform. Such a z-transform is determined to within a constant multiplier by its zeros and its poles. For this example, there is one zero, at z0, and one pole, at za. The pole 0 plot and the rock for example 3.1 are shown in figure 3.3 where the symbol 0 denotes the 0 and the symbol x the pole. For lot I2, 1, the rock does not include the unit circle, consistent with the fact that, for these values of a, the Fourier transform of the exponentially growing sequence annulm does not converge. Example 3.2 Left-sided exponential sequence. Now let x New Jersey anu n-1 and n-1 and gt-1. Since the sequence is non-zero only for n, this is a left-sided sequence. The z-transform in this case is 0 0 1 x, z, equals L anu n-1 jz n L n equals 0011 equals -0 0, 3.15, 0 0 0 0 log n z n1 L, a1 z, slash L. N equals 112 equals 0 if log L, 1 lt lor, equivalently, is L lt lal. The last sum in EQ, 3.15, converges. And using again the formula for the sum of terms in a geometric series, 1 1 z x, z, equals 1-1 underscore a 1 z 1 z a is L lt 14, 3.16, the pole 0 plot and rock for this example are shown in figure 3.4. Section 3.1 Z-transform 105 Note that for lal lt1, the sequencia flu n1 grows exponentially as n-+-0 0, and thus, the Fourier transform does not exist. However, if log igt1 the Fourier transform is 3.17, which is identical in form to EQ, 3.14. At first glance, this would appear to violate the uniqueness of the Fourier transform. However, this ambiguity is resolved if we recall that EQ, 3.14, is the Fourier transform of a flu n if lal lt1, while EQ, 3.17, is the Fourier transform of underscore n un1 when lal gt1. I'm z-plane 1 refigure 3.4 pole 0 plot and rock for example 3.2. Comparing x 3.12 and 3.16 and figures 3.3 and 3.4, we see that sequences and, therefore, the infinite sums are different. However, the algebraic expressions for x, z, and the corresponding pole 0 plots are identical in examples 3.1 and 3.2. The z-transforms differ only in the rock. This emphasizes the need for specifying both the algebraic expression and the rock for the bilateral z-transform of a given sequence. Also, in both examples, the sequences were exponentials and the resulting z-transforms were rational. In fact, as is further suggested by the next example, x, z, will be rational whenever xn is a linear combination of real or complex exponentials. Example 3.3 Sum of two exponential sequences. Consider a signal that is the sum of two real exponentials, xn equals, n earn plus, underscore, n earn. 3.18, the z-transform is, 3.19. Chapter 3 The Z-transform 106 DC1 equals L, 1 ZZ L, N plus L, 1-3Z, N equals O N equals O 112, 1 is 1, colon plus, colon, dash 1 C1 1 plus CL, 1 1 C1, 1 plus CL. 2Z, Z is, 3.20, ZD, Z plus, for convergence of X, Z, both sums in EQ, 3.19, must converge, which requires that both LLT1 and 1, dash, LLT lor, equivalently, is LGT1 and is LGT. Thus, the rock is the region of overlap, is IGT1. The pole zero plot and rock for the Z-transform of each of the individual terms and for the combined signal are shown in figure 3.5. A, B, figure 3.5 pole zero plot and rock for the individual terms and the sum of terms in examples 3.3 and 3.4. A, 1/1-R1, is LGT. B, 1/1 plus 1 R1, is LGT1. C, E, 1/1-R1, plus 1/1 plus 1 Z1, is LGT. Section 3.1 L transform 107. In each of the preceding examples, we started with the definition of the sequence and manipulated each of the infinite sums into a form whose sum could be recognized. When the sequence is recognized as a sum of exponential sequences of the form of examples 3.1 and 3.2, the Z-transform can be obtained much more simply using the fact that the Z-transform operator is linear. Specifically, from the definition of the Z-transform in EQ, 3.2, if xn is the sum of two terms, then x, z, will be the sum of the corresponding Z-transforms of the individual terms. The rock will be the intersection of the individual rocks, i.e., the values of z for which both individual sums converge. We have already demonstrated the linearity property in obtaining EQ, 3.19, in example 3.3. Example 3.4 shows how the Z-transform in example 3.3 can be obtained in a much more straightforward manner by expressing xn as the sum of two sequences. Example 3.4 Sum of two exponentials, again, let xn be given by EQ, 3.18. Then using the general result of example 3.1 with a equals na, the Z-transforms of the two individual terms are easily seen to be 1 1, Rn 1 1 minus 1 is ilk 2, 3.21, minus 2, z, irz, 3.22, minus 3 Rn 1 is ilk 1 1 plus 3 and, consequently, 1 1 1, Rn plus, dn Rn plus is ilk 3.23, Ile 1 plus 2 2 as determined in example 3.3. The pole zero plot and rock for the Z-transform of each of the individual terms and for the combined signal are shown in figure 3.5. All the major points of examples 3.1 to 3.